Hello, my name is Chris Deering and I'm the Field Application Engineer here at Concurrent Technologies. As some of you may know, Concurrent Technologies, we design, manufacture and test our own SBC or single board computer cards based on Intel processor technology. This is all done at our in-house design and manufacturing plant based at our head office in Colchester, Essex in the UK. These SBCs come in a varying number of form factors, or backplane formats. We cover VME, compact PCI, AMC, VPX, and to complement that we also have XMC plug-in modules, I/O plug-in modules that can be fitted to a number of these SBCs. We also can put together development systems for customers, helps them get up and running very quickly without worrying about how all the hardware. So today I want to talk a little bit about self-encrypting drives, or SEDs for short, what they are, how they're used in our products, and how an embedded system can start up when fitted with one of these devices. One of the technologies that goes hand in hand with our SBCs is the storage device itself. This is also used to install and run the operating system, the user application, but more importantly it can be used to store information that the application is reading or is using. This could also be confidential or valuable information. That's all stored on the same drive. Storage technology in recent years has advanced considerably, both in terms of storage capacity, but also in access times, both read and write have gone up considerably or decreased considerably. But also this has led to new technologies that a few years ago wouldn't have been available without a great deal of software and expense. So there's been quite a lot of improvements in this area. So this leads us on to one of the technologies widely available that we use on our SBCs, Concurrent Technologies, and that's the NVMe M.2 based drive, and also the older SATA solid state drives. This new technology can potentially bring Opal 2 compliance, which allows for self-encrypting drives. So that's a key benefit to a user where they want to secure their data at rest. So I'll just talk a little bit about how a self-encrypting drive works. Basically, once the drive has been unlocked, once it's been given a password or phrase, and it's unlocked, all the data that's written to it and is encrypted, and all the data that's read from it is decrypted. This is all taken care of by the encryption engine which is built into the hardware controller of the drive. So there's no degradation to performance with regard to the user application or the CPU. It's all done within the hardware of the drive, which obviously this makes this operating system independent. So it doesn't matter whether you're running a Linux or Windows or VxWorks or any other type of operating system. It is independent of the OS. So now I'd just like to talk a little bit about the different formats that are available and what we can supply. Here we've got a couple of examples. The top left here we have the NVMe based M.2 module. This comes in a couple of sizes. You've got 42mm or 80mm sizes. And then down below on the left here we have a traditional SATA solid state drive, 2.5-inch drive, but this is an Opal compliant, 2.0 compliant drive, so it's self-encrypting. And we've also recently designed and produced our own ruggedized VPX carrier card that allows 2 removable M.2 modules, which is obviously very useful for a ruggedized environment to remove physical drives. So, as mentioned, to be able to unlock the drive, you need to be able to enter a password or a passphrase. Traditionally, there's open source utilities out there that allow this to happen, but obviously it requires a keyboard for the user to enter the details. So that's not going to work with an embedded system, or unlikely to work with an embedded system where you need there's normally no user interaction at startup. So ways to get around this is potentially to have a remote authentication server connected via a secure Ethernet connection to the host. The host requests the authentication details for the drive from the server, and then it will unlock the drive. This obviously has a downside of it needs an Ethernet connection and also a remote server, which just may not be within your design of your system. So that may be a non-starter. Another potential way around it is to have a USB key that's got the details secured on it. This is plugged in at system startup, potentially remotely if you've got a remote system. But obviously still, once the system's booted, still required to be removed. So there's still some user interaction there required, although not obviously in a keyboard in this instance, but still needs some human interaction. So moving on, lastly, another way around this potential issue is to store the details within a secure device on the single board computer, i.e. a TPM device. All recent concurrent boards, SBCs, come with a TPM 2.0 device fitted, so an ideal candidate for storing the authentication details. These can be stored with other measurements of the board, so you could lock that particular drive to that board if you so desired. You can make it quite complicated, but it's a potential way of starting up a system without any user action or interaction, I should say. Just a little bit of word of warning with regard to self-encrypting drives. It only protects the data on the drive when there's no power. If the drive is removed from the system and put into another system without that password authentication, the drive won't become unlocked. So it's only protecting data at rest or that's been power cycled. Once it's been unlocked, that drive is then available like any other normal drive, so the data is readable in plain text format. So you need to build in other security measures within your system, access to the equipment and so forth. It doesn't protect everything all the time. It's only if the drive was stolen and people didn't have the details to log in, then it's obviously safe. So it's just a little word of warning there, these drives. So now I'll just move on quickly to how a self-encrypting drive starts up within a system. With an embedded system in this instance. Basically the host at PowerUp is presented with what's known as a shadow master boot record. Within this record or partition it is what's known as the pre-boot authentication image. And this is normally just a cut down version of Linux with enough code in there to get the authentication details from the user and pass that through to the drive. And it doesn't do any more. And once the drive has been unlocked, that shadow partition disappears, and the real partition, the real MBR, is presented to the host. So normally, after it's been unlocked, you would reboot the system, and then that partition is available. You then boot your whatever operating system or application you want to from the unlocked partition. If it was another Linux-based system, you could actually use the pre-boot authentication image to just download the new kernel from the real partition, download the root file system, and then you can execute the new kernel. So thus bypassing a reboot and saving time, which is obviously quite beneficial in an embedded system, your fast startup. So that's a quick overview of how a system would start, or how a system would start when fitted with a self-encrypting drive. And as I say, the authentication key can be entered using various different methods. And because this is quite complicated, we've produced a couple of application notes which would help our customers, end users, but initially just how to set up a self-encrypting drive, but also how to get the information from a TPM. So we go through the whole process of building a pre-boot authentication image to allow access to a TPM, because this is quite a complicated process. So if there's anything that we can help you with regard self-encrypting drives, how to initialize them, how to start up an embedded system, please don't hesitate to contact us via the website or via your sales representative, and we'll be more than happy to help you out with anything in this regard. So thank you very much for listening, and goodbye for now. Thank you.